So in dealing with this problem, this is actually a problem that you've seen come up on some of the computer practice, at least in one form or another, but we're kind of bringing it together here, tie a bow around it, make sure we got all the stuff taken care of on it. First of all, notice that we're decreasing by a percentage. And anytime you increase or decrease by that percent, it's telling you that you got to be using an exponential equation. Specifically this one that we've been using here for a while now. So if I am going to start plugging into this equation, I'm typically going to do A of t equals P. What is our P value? What's our starting value, remember?
5,000.
That's the 5,000, yes. So it's going to be 5,000 times 1 plus R. What is R here?
0.0188.
Well, it is our percent, but I turn it into a decimal, and 8% is a decimal. You take the percent, divide it by 100. That's going to give me 0.08, but I'm decreasing. So it's like my rate is negative, but I don't really want to write plus a negative. That's just not as tidy as it could be. So that's why when we're decreasing, we subtract. And then that's going to be to the power of t. Do I know what t is? No, we don't know what t is. And yet there's still something in here that I haven't used yet, this 3,000. That really should appear in this equation since I'm trying to figure out when it hits 3,000. So where does the 3,000 go in this equation? Yep, it goes in for a. So instead of a of t equals then, we do 3,000 equals. This then is the equation that we're going to solve. And we solve it just like we would pretty much any other equation. I'm going to start by going ahead and doing the 1 minus the 0.08. That gives me a tidier number in there to work with, the 0.92. And then go ahead and divide both sides by the 5,000, because it's 5,000 times it, and I'm doing that multiplication. And so I have 0.6 equals 0.92 to the power of t. Well, we're going to solve this then. I'm solving for an exponent. What do I use to solve for an exponent? Logarithm. Absolutely. Remember, that's why logarithms exist. Logarithms exist solely for the purpose of solving for an exponent. So I rewrite it in log form. This then is a value I can calculate. Before I put up how we do it and what we get out of it, then take a moment, calculate that value so we can make sure that you remember how to calculate that, because we're going to be doing that sort of thing a lot today. All right, now to calculate, hopefully you're thinking about that change of base formula where we have to do log divided by log. The base always goes on the bottom, meaning that in this case it's going to be log of the 0.6 over log of the 0.92. Every now and then I'll see somebody who will remember how to go from here to here by remembering, oh, the big one goes here. I wouldn't do that in terms of like which number is a bigger number than the other one. But certainly if you want to remember in terms of, well, the little one as in it's written little goes on the bottom, that would make sense. But you do need to be able to do that conversion or be able to find the answer, which is about 6.13 or 6.1. We didn't specify what to round to here. So it takes about 6.13 years for the population to fall below 3,000. All right, now that problem and every other problem that we have been doing like that, they've all been annually compounded interest. But not all interest is compounded annually. In fact, typically it's not compounded annually. It's compounded on smaller intervals. And so that's what we're going to be taking a look at today. In order to take a look at that then, we need new notes. You'll notice that this formula is actually very similar to the one that we've been using. The only difference is that we now have the n in there. In fact, this formula is the same formula if n equals 1, which is once per year. So we're going to be using that formula in this example problem. Now, the critical information that we have here, we start by putting $1,000 in. So that tells us our p-value. It pays 1.2% per year, so that tells me my R value, I'm going to be doing 1.2 divided by 100. R is going to end up being 0.012. But the interest here, notice, is compounded monthly. That actually tells us what my N value is going to be. What will N equal here? Well, remember, N is how many times it is compounded per T. T is measured in years here. Monthly is how many months per year? 12. So in this case, that tells me that N equals 12. And we want to know the value of the account in 5 years. The 5 is going to be my T value. So I go back to that same equation that you just put into your notes, and I can plug those pieces in there. And you can see this is what it looks like then when we plug everything in those spots we just talked about. And then from here, once we have the equation at this point, then we're just simplifying. So like anytime we're going to simplify these, I want to go ahead and I want to take care of the stuff inside the parentheses first. For this first problem, I chose nice pretty numbers because the 0.012 divided by 12, that just equals 0.001. It's going to make life a little bit easier. And the 12 times 5, since that's kind of up on its own in the exponent, I can do that as well. So this is the equation I'm going to actually calculate the value for. 1,000 times 1.001 to the 60th. Okay, so then we calculate it. We do the 1.001 to the 60th, multiply it by 1,000 using the normal order of operations, and you should get an answer here of 1,061.80, which means that after 5 years, by compounding monthly, we got up to $1,061.80. Now, how did the monthly change the numbers then? When we were just doing this annually, if we'd done it using the compounding annually equation, we would have ended up with 1,061.46. So notice we got a bigger number by compounding more often. Well, that's good, right? We got more money out of it. Is it a huge amount here? No, not on this one. It's not a huge difference. But the nice thing about compounding interest is that the more often that compounds, the bigger that difference is going to be. This was a fairly small rate. We're going to now take a look and see what happens with some bigger rates as well. So go ahead and write down the critical piece of information for this problem. And then having worked through that last one, seeing that example, I think you can go ahead and work it through. Or at least take it as far as you can at this time. But see if you can take it all the way to the end, get the final answer. And so when you go to start writing this equation, this is all the stuff that we've used before. The p-value is 200. Our rate becomes 0.06 because I turn the percent into a decimal. But it's got to be over n. What is n in this particular problem going to be then? It's compounding daily, so it's really a question of how many days are there per year. 365. And notice that n appears twice in the equation, so the 365 appears twice in our equation. From there, once you have the equation set up right, go ahead and calculate your value. Now in terms of doing that calculation, if we do the stuff inside the parentheses, it gives us a decimal in this case. And it's one of those decimals that we can't just write the whole thing down because it's going to be repeating and going on. And so in order to then calculate this value, you do this calculation to get this number. And then just leave that number sitting up on your calculator and say to the power of 7,300. You don't have to retype it in that way. You then are using the exact number, and you don't run into any rounding error as a result. Because rounding error with exponential equations will kill you because the error gets compounded every single time. And that would be a bummer if an error was compounded 7,300 times. But when interest is compounded 7,300 times, we're okay with it. You should be getting an answer of 663.96. So our $200 investment became $663.96 in 20 years. Now, a little side note as you're making note of that information, making sure you kind of get where everything came from. We're talking about a lot of detail-y kind of stuff here and being very exact. We're talking money, so we go out to the 100th place. But I just do want to point out and remind you that, the 6% interest per year, unless it's guaranteed to be exact 6, our number is probably an estimate. If this was like a stock or something that varied but averaged 6%, our number would be close to that, but it wouldn't be exactly that. So realize that there is some play depending on how solid the numbers are that you're actually working with. Then now put that into practice on these problems. I'd like you to please take this same situation, but compound it annually, monthly, and then daily. And then think about what continuously would mean, because that's actually where we're going to stretch this idea to the idea of continuously compounding interest. So as you're working these, and you do that first one, the annually compounding interest, annually, that means it's compounding once per year. You could use our new equation and plug 1 in for n, or remember that just means it's the same as the equation we've been using for a week or two now. So you could just revert back to that same one for annually. And so for annually, you end up doing 1.1 to the power of 15. That's having simplified a few things first. Times the 2,000, and you get 8,354.50. And again, I'm going out to the 100th place because we're talking money, so I got to the cent. So now on to monthly. For the monthly compounding interest, that means we do need to use our new equation. Our n value here is going to be 12. But the p and the r and the t are all the same. It's just that now n equals 12. So in this case, we end up getting 8,907.40. So notice in this case, there's actually a very dramatic jump going from just annually compounded to monthly compounded. So going from here to here, notice we actually got quite a bit more because it was compounded more often. The bigger the rate and the longer you leave it there, the better off you are. All right, and then for daily, it's the same idea as we did for monthly, except here n equals 365. And so we end up doing 1 plus the 0.1, our rate, over 365, that's where this number comes from, to the power of nt. So 365 times the 15 years. And so in this case, we get 8,961.54. Again, notice it increased. The more often we compound our interest, the more we get out of it, because you're letting it grow upon the growth more. But you'll notice that the jump from 12 to 365, in terms of the raw final amount, wasn't quite as dramatic as it was going from just compounding once a year to 12 times a year. And so there is basically a limit to just how big this could get. But you can see how we can make n bigger and bigger, right? And that's kind of the idea behind continuously compounding interest, because continuously compounding wouldn't be compounding 12 times per year. It's continuously compounding. So it's not even compounding every day. It's not even compounding every hour or every minute or every second. It's continuously compounding. So it's not like at this moment you have this and then at this particular chosen time it goes up again. It's almost like this idea of continuously compounding interest is saying that we're compounding basically an infinite number of times within that interval. Now the interesting thing is, though, that since you can see that these values start kind of leveling out, they're only going to get so big. No matter what I make my n value, no matter how big I make it, this is never going to reach 1 million or something crazy like that. So there is actually a limit here, and that limit has to do with another special mathematical number called E. More notes for today. Because if we're going to deal with continuously compounding interest, we end up including this mathematical number e, which has a bunch of interesting properties. One of which, though, is that it actually can help us find that limit as something is approaching infinity like this. All right, and then since this includes this value here, I'm not going to be expecting you to type that value into your calculator. It comes up so often, just like pi is an irrational mathematical constant that comes up a lot. E comes up so often that it also has a button on your calculator. Many calculators actually have the button. They don't even bother putting an E button on a lot of them. They'll actually have an e to the x button. If your calculator has one of those, like if you wanted to do e squared, you would enter 2, and then you would press that e to the x button. And that would give you e squared. If you're doing it on a graphing calculator where it actually displays what you type in, it'd be the other way around. You press the e to the power of whatever it is button, and then you'd tell it make the power 2. But again, it depends on your particular calculator about how it displays. Now, having seen that new equation, we can use that in order to now write the equation for a continuously compounding interest. So again, I write it as a of 15, and it equals p. That p value is the same p value as what we've been using all along, so it's still 2,000. It still represents our principal, starting amount. But in this case, instead of parentheses 1 plus whatever, it's 2,000 times e. Remember, e is a number here, just like pi. But we don't want to write the whole thing down because we can't write the whole thing, so we just write e. To the power of rt. R is also the same thing as what we've been using all along. So I take my percent and turn it into a decimal. So 10% as a decimal is 0.1 times t. And t in this case is 15 years. So now that I have my formula, I can now start looking at how would I calculate it. Well, the first thing I'd want to do in making calculations here is actually just figuring out what does this exponent equal. What is 0.1 times 15 going to give me? Well, thankfully that's a nice pretty number. It's just 1.5. So I now have 2,000 times e to the 1.5. Now it's calculator time. We got to do the exponents first, so we have to do the e to the power of 1.5. Then once you have that number, take the whole number, don't round it, but take the whole number and multiply it by 2,000. You should get an answer of 8,963.38. Like you now do it on your calculator, make sure you can get that number out of your calculator so that you know how to use it for these problems. All right, so we're now going to be taking a look at how to solve these. Just worry about the first one at the moment. 2e to the x equals 800. Well, first up, let's go ahead and get that exponential part by itself first. So that means getting rid of the 2. So we go ahead and divide both sides by 2 there. So I now have e to the x equals 400. I now need to solve it for x, which is in the exponent. What do I use to solve for an exponent? Log. And so if I wrote this in log form, then I'd be writing it as x equals log base e of 400. But e is a tricky number to work with. I don't really want to have to go and find that e button every time I do one of these logarithms and have to put that into the change of base. Especially because actually in various calculations, this calculation gets done a lot. Log base e comes up a lot. In fact, it comes up so often that it has its own special little function. So again, some notes here. Basically, this just says that log base e of x is written as ln x. Means natural logarithm. And yes, when you write that ln x, make sure you're writing it as an L. Make it a curly L if you need to, so that you don't think it's a 1. And so now we know that anytime we're having to deal with something that would become log base e of x, I'm actually going to turn it into ln of x. So now let's go back to that problem we were just looking at. But now notice how the work has changed. instead of x equals log base e of 400, I'm now going to do x equals ln 400. That is the natural logarithm of 400. And so to calculate this value then, you're actually just going to go to your calculator and input natural log of 400. Now to make sure you get the right number out, you should be getting an answer of about 5.99. When you go and look for this button, usually the ln button is close to log, and you probably will also find it very close to the e to the x button that you were just using, because they're very closely related, right? E to the x and ln of x are inverses of each other. And then from there, let's go to the next problem over. Let's do the ln x equals 5 and see how we had solved that equation. So, in order to solve the natural log of x equals 5, at first, you won't have to do this in the long run, but at first it might help you to take your ln x and rewrite it as log base e of x. It'll just help you to visualize how we change it, because I'm going to take that log base e of x and I'm going to write it as an exponential. And so as an exponential then, it becomes the base e to the power of, remember log equals the exponent, so it's going to be e to the power of 5, equals x. Now, certainly writing it in this form certainly helps as you're getting used to natural log. But you don't have to. In fact, you could go straight to this x equals e to the 5th, or e to the 5th equals x. It means the same thing. And then you can just calculate that value using that e to the x button that we were just using earlier. And so we get x equals 148.41. We'd use the same process to solve these other two.